Okay, so for the final talk today is from Lebovitz from Chicago, and he'll tell us on models about the subcritical boundaries, the things that we've been trying to find with edge states and others.
How do I do this? There we go. I'm going to tell you about finite dimensional dynamical systems. Why? My own motivation is that this explanation of transition via dynamical systems involves a basin of attraction, because the underlying stability problem gives you linear stability. And in some problems, in a number of problems, different from this one, that basin is quite complicated. And I'd like to have some feeling for what it looks like, ideally for high-dimensional dynamical systems. But since I didn't know what they looked like for low-dimensional dynamical systems, I've been looking into that, and that's what I'm going to tell you about. I think most of you know the basics for forming finite dimensional dynamical systems in this context. Let's see. I have my own weapon. You get a differential equation, an autonomous system of equations, with a linear part, which is strongly stable and contains the Reynolds number parameter, and you get a quadratic term, which conserves energy. And you can derive this from Galerkin approximations to the Navier-Stokes equations under certain mild assumptions. You could quibble with the assumptions, but I don't want to do that, not today anyway. Any such system has a basin of attraction, which is an invariant set, and its boundary, if it has one, is likewise an invariant set. So in one of the scenarios, the self-sustaining scenario, at least in its transition version, the picture is this. You have the origin of coordinates represents the stable laminar point. This green mesh represents a cartoon of the basin boundary. On that basin boundary, there is an equilibrium point, which is unstable, usually referred to as the lower branch equilibrium point. Its unstable manifold goes off in this direction, and if you start near the threshold region, that is the point on the basin boundary that's closest to the origin of coordinates, then if you start exactly on that point, then that point will be attracted to this point U, which is, so the basin boundary and the stable manifold of U are one and the same. If you take a point which is just above, then it will get captured by this stable manifold, and it's off to the races. And what the races are is another matter. So here's a two-dimensional system which satisfies those conditions. And the red curve is the basin boundary. It behaves exactly as in Wallef's scenario. Here's an orbit, this blue one, which goes off to large distances. The bypass scenario is to some degree represented here as well, because orbits that lie just below the basin boundary have this large excursion behavior. And the only difference between this and the linear bypass scenario is that these orbits enter the origin on the ingoing segment of the unstable manifold of this lower branch equilibrium point. But what I want to call to your attention is the global structure of this basin boundary, and that's on the next slide here. It's this snail-like region. The interior is the complement of the basin of attraction. That is to say, if you manage to start with initial data in this interior, then orbits remain there permanently and get attracted to this upper branch equilibrium point, which was not visible on the previous trajectory, previous slide. The previous slide included only this tiny region over here. I want to emphasize that the upper and lower portions of this basin boundary come together in a very narrow sort of double layer here. And for this problem, this two-dimensional problem, it's easy to resolve this double layer. But in other problems, it's harder to resolve it. So let me leave this two-dimensional problem and go to some models also proposed by Wolof, which probably a number of you have seen. They've been studied a fair amount. This is a four-dimensional system. Delta is the reciprocal of the Reynolds number. There are 8 constants in here. It'll make you sleepy to look at them all. You don't need to look at them all. They're usually given certain canonical values that were derived via some Galerkin truncations a long time ago, and they have some special properties which are indicated in these other remarks. If you look at the equilibria, you put all the x dots equal to 0, and you just plot the norm of equilibrium versus the Reynolds number, and you get this diagram, this familiar looking diagram. Laminar solutions down here are stable. The lower branch solutions are here. They have the right kinds of properties. That is to say, every one of the lower branch solutions is unstable with a one-dimensional unstable manifold and a three-dimensional stable manifold. So if you go back to Wolof's picture, I wanted to ask myself a fussy mathematical question. The fussiness comes from the following, that if you define the basin boundary, well, it's defined in a certain way. If you define the stable manifold of an equilibrium point, it's defined in a different way. There's no law of nature that says that the two need to be one and the same. But they turn out to be the same in a lot of models. The two-dimensional model that I showed you, some other models that have been in the literature, 2, 3, and 4-dimensional models, and all of them, they seem to be the same. I just wanted to ask the question, is that true here? And it turned out that for the case that I've studied, and I've only really studied in detail one value of r, it is not the case. If you start here at a transition at this threshold point and use that as initial data and ask whether it is attracted to this point u, the answer is no, it isn't. It is attracted to a periodic orbit that lies elsewhere on this basin boundary. So I can show you a little bit of that. So this is for a value r equals 145. You have to start with a point on the basin boundary. These points were calculated in pretty good approximation by Carlo Cosu a couple of years ago. And by refining them so that I get 2 points, one just above, one just below, very close to one another, say 10 to the minus 12 or something like that, I forget, and integrating either of them, with either of them as a starting point, I get first a transient for a few hundred units of time, and then it settles into this kind of periodic orbit, remains there for a long time, like 16,000 units of time. And then it either decays and is captured by the upper branch equilibrium point. In other words, it spirals into that one. That's if it lies outside the basin of attraction. Or if it lies inside the basin of attraction of the origin, then it decays to the origin. So I wanted, I'll show you some more pictures of that if there's time. But it raises the question, what role is being played by this upper branch, by this, lower branch equilibrium point? What role does it play? So what happens near this point is something which at first I said is not possible. If this were true with exact mathematical accuracy, it would be not possible. If you start with an initial point, which is the lower branch point, plus a small perturbation. In this case, the perturbation is taken in the direction of x4, but it doesn't matter what direction you take it in. I've taken it in other directions too. As long as the direction is transverse to the basin boundary, it should be that for one sign of v, orbits will decay to the origin, and for the other sign of v, they will be permanently bounded away from the origin. But for whatever, this is for v equals 10 to the minus 10, all orbits decay. Some orbits decay directly to the origin. Others go through a little agony first, but then they decay to the origin at a slightly longer time scale. All orbits are decaying. How is this possible? Well, let me remind you of that 2D example. In the 2D example, these two segments of the basin boundary you could not distinguish by eye, so I've drawn a cartoon separating them. But bear in mind that these are very close, say 10 to the minus 8, 10 to the minus 10, something like that. If you were looking for these with a grid numerically, you would not find any points that, that were attracted to this point S. In other words, all the points you would find would be in the basin of attraction, and they would either decay directly or they would surmount this obstacle and decay after a longer period of time. So my question to myself was, can that be happening for this four-dimensional system? And in order to investigate that, you could go to higher precision arithmetic, but I was afraid on the basis of estimates from the two-dimensional problem that it would be possible to defeat quadruple accuracy and octuple accuracy. And so I approached this in a different way. First, I simplified Walleff's problem by putting all of his parameters, his carefully chosen parameters, equal to 1, with one possible exception, this sigma 1. If I put sigma 1 equal to 1 and look at lower branch solutions, which are indicated here, I find exactly the same anomalous behavior that I just described, that no matter where I start, no matter what perturbation I take from that equilibrium point, orbits decay. So the idea was to try to, if there is a gap that I can't find with usual double precision arithmetic, can I open up the gap by re-choosing this sigma 1? Let's say starting with 0 and then going to other values. And that was the strategy. That strategy does seem to work, and I want to explain to you what you're going to see on the next diagram. In order to explain it to you, I need to show you the basin boundary in the neighborhood of a lower branch equilibrium point. Of course, that's a three-dimensional surface and four-dimensional space. I don't really know how to show it to you, so I have to explain to you what it is you're going to see on the following slide. So this is for sigma 1 equal to 0. I haven't changed R. In these cases, for this simplified model, I just left R equals 15. What you're seeing is the intersection of the basin boundary with a hyperplane, x1 equal constant, x2 equals constant, and the constant values of x1 and x2 are those appropriate to the lower branch equilibrium point for these values of sigma 1 and R. So this point lies in this hyperplane, and in terms of x4 and x3, it lies over here. The origin is over here. The quotes around it mean that that's not the origin. The origin isn't in that plane. So that's a projection of the origin on that plane. And so I just use that notation. So here, certainly the gap is huge. I mean, if I take a point, take this point and I move it inside a little bit, this is the complement of the basin of attraction. And a point that starts out here will be attracted to the upper branch equilibrium point. And a point on the outside will decay to the origin. So indeed, I've opened up a gap. This is a local neighborhood of the lower branch point to see a sort of a global version of the basin boundary. The previous diagram showed you a little strip right down here. It's quite extensive, and it has this funny shape. Most of the phase space lies in the boundary, in the basin of attraction, and the complement is also sizable. This is another view. This is x4 versus x2 with x1 held fixed at the lower branch value and x3 held fixed at the lower branch value. And if I continue, one more view of this, this is x1 against x4. Here x2 and x3 are held fixed. So this is fairly complex. Here's the basin of attraction. Here's its complement. Here's the basin of attraction, its complement, and so on. And here's what looks like the beginning of a gap. But the lower branch equilibrium point doesn't lie in that gap. It lies far from it. It lies out here. So if I make a little perturbation upwards, I'm in the complement of the basin of attraction, and such a point will be attracted to xub. No anomaly here. So let me increase sigma 1. So I've increased sigma 1. It's now this value. The lower branch equilibrium point is closer to this gap. And what you can't tell, but I can tell numerically, is that the gap has narrowed. It's now smaller. If I I have a lot of these, but I'll cut to the chase here. This is 0.185. It looks like the lower branch equilibrium point is right on top of where these curves come together. It's not quite true. If I show you a blow up of this region, it looks like this. So it's getting very close, and this gap has become extremely narrow. And my algorithm for finding these points fails when these two come close together. That's a failure that could be corrected. But in any case, it fails out here because they've become too close together. If I go up a little farther, 1.6, it fails out here. It's getting very close. If I go to 1.9, a topological transition has taken place. If you're interested, I could talk more about this. But I don't think this is... anyway, I cannot resolve this double layer here. I believe it is a double layer. I can detect it in the way that you detect the edge of chaos. At least I believe it's the same way. And that orbits above here take a long time to decay, and orbits below here decay directly to the origin. So it's like that double layer, which is your edge of chaos, contains a little teeny weeny strip of the complement of the basin of attraction. That's sort of, I shouldn't press that too hard. That's a guess at this point. Anyway, that's interesting. I find it mathematically interesting. What does it say for the dynamics? For the dynamics, it says maybe you shouldn't be looking in that region of phase space because all orbits are going to relaminarize there. But there is a region of phase space where orbits do not relaminarize. So that's a preliminary conclusion. Let me, if I have a minute, show you a little bit more about the basin of attraction near the threshold point. So this point T is, at least approximately, the closest point on the basin boundary to the stable equilibrium point. And here's what the basin boundary looks like here. And if you look at the scale, this distance from here to here is about 10 to the minus 6. The distance of this point from the origin of coordinates is about 0.1. So if you were trying to locate this little nose of region to get outside of the basin of attraction of the origin, you have to be extremely accurate. You're probably going to miss. And you probably only find it when you get farther into the basin of attraction. And if you start a point here, well, this is a repetition. If you start a point here, there's a transient. It goes to a distant region. Here, this is a slice through the upper branch equilibrium point, because this periodic orbit, which establishes itself, encircles the upper branch equilibrium point for a long time, and then either spirals into it if the original point was outside the basin of attraction, or then goes away back to the origin, which is off this way. So conclusions, if there is a moral to the story, I'll concede it's a big if because I've only looked at one four-dimensional model. I think this is fairly safe. The structure of the basin of attraction may be quite complex. I don't think there's any question about that. For some low-dimensional models, maybe the lower branch equilibrium point is not so significant. I wouldn't want to extrapolate that to PDEs in this audience, but I suppose it's something to think about. And then orbits in the basin of attraction, they can relaminarize with arbitrarily long periods of relaminarization, depending on how close they start to the boundary of the basin of attraction. Okay, thank you.
Thank you very much for this very interesting discussion of the low model.
What characterizes lower branch?
Well, I think that the name probably originated from this diagram that I showed of equilibrium solutions, where the lower branch equilibrium solutions are those that are closer in norm to the stable laminar point, and the upper branch solutions are farther away. But somebody more steeped in the subject might want to contradict that. That's the only.
The other characteristics is the eigenvalue. The lower branch is sort of presented with one more.
Do those characteristics play a key role in the argument that
It's hard to know that. I mean, they certainly played a key role in my surprise that all orbits near the lower branch point relaminarized, because I expected that there would be a direction. After all, there's an unstable manifold. It's got to be really teeny. So only to that extent.
I mean, can you guess, make a guess on why that complement gets wispy? I mean, is that a general property of?
You saw it in the. I picked the two-dimensional example because it had that property, and what the two-dimensional example and Wallef's models have in common is that they have an invariant hyperplane. In the two-dimensional model, it's a line, was the x-axis. In Wallef's models, it's x4 equals 0. And the Navier-Stokes equations have invariant subspaces. I mean, there are the stable solutions which are independent of the span-wise direction, for example. I think they should be reflected in the low-dimensional dynamical models or the high-dimensional dynamical models. They will be in the models of John Gibson and Predrag because they're using basis functions which reflect the symmetries. And whenever you do that, you will find these. So those play a key role.
Near the critical state, if you used, let's say, over a narrow range, random initial conditions, then from the diagrams that you have and from what you would generally tend to go to either one of those attractors.
No. I mean, when you say the critical,
Yeah.
If
you go back to your original diagram.
This one or farther?
Well, you even had the one which was very general.
Yeah.
Well, anyway,
Yeah.
what I'm trying to see is whether the results become more robust or less if you had a distribution of initial conditions, more narrow distribution.
If you had a distribution of initial conditions near here, you would find things relaminarized. But if you go beyond that, and for r equals 145 in Wallef's model, you're beyond that, then you're over here, and if you distribute initial conditions here, everything will relaminarize. I mean, with extremely low probability, would you find a point which lies in the interior of that double layer? And only then would the orbit fail to relaminarize. So all the orbits will relaminarize if you take random initial conditions here, but ones that start out above will go the long way around and take a longer time to relaminarize. Ones that start out below will relaminarize more directly.
Can you go back to your original diagram, very fast one that you used?
I can try. Tell me when to stop.
You have one. For example, the next one that you have.
This one?
Yeah.
Yeah.
Now, here you have basin there, which is B, in a region
Yeah.
where the solution can be different, in and outside.
Solution in here, this is the basin of attraction of the origin. So if I start a point here, it goes around and comes over here. I can only get into this point from this region of phase space if I start in here. And that,
So if around that point you had a small distribution,
yes,
so what would happen? You would have some trajectories which would go one way and some trajectories which would go the other.
yes, exactly, but they'd all relaminarize. I mean, I would have to be very lucky to find a point which lies in this region, and therefore it stays in this complementary set.
The argument is that small means 10 to the minus 10 and less.
Yeah,
So it has to be very narrow and very localized.
yeah, that's right.
Ivarka?
Yeah, in the four-dimensional model, what are the dimensions of the unstable manifold? How many unstable directions does the lower branch have?
One.
Just one.
Maybe another quick question?
Yeah, could you say a little bit more about the pinching off bifurcation?
Oh, yeah, let's see if I can do that here. So, if you look in books which discuss this equation, this equation of curves in the plane, parameterized by C, the generic unfolding is these three. If there's a particular value C star, so that this represents a pair of curves that cross, and the generic unfolding is, if you take C less than C star, you pull those two apart, north and south, and if you take C bigger than C star, you pull them apart east and west. But in what is, for me, the real world, you don't have this nice, clean picture. You have a couple of curves that look like this. Here, the gap between them is very small. When they come together, the gap is still smaller. And when they've separated, the gap is so small, my algorithm doesn't pick it up. So that's it.
Maybe I can rephrase my question. Can you recognize this bifurcation from the unstable and stable directions of the large point?
I'm trying to look into that myself. The first,
No, there must be some degeneracy.
well,
It's a global degeneration. You're not going to pick it up from an eigenvalue.
there are two possibilities. There are two possibilities here. One possibility is that there is no singularity on in the basin boundary. One possibility is that the singularity is an artifact of looking at slices through it. I can give you three-dimensional examples like that. But
Have I misunderstood the
Sorry. Okay, I'm sorry, but I find this fascinating, all of this discussion. But if we continue going, there won't be any dinner tonight.